Welcome to The Explainer. If you've ever wrestled with a tough physics problem book, you definitely know the name Irodov. It is absolutely legendary. So today we're going to dive into one of those problems, a real classic on gravitational potential energy, and we're going to solve it step by step.
So here's how we're going to break this down. First, we'll get a solid handle on what potential energy even is. Then, we'll knock out the simple part of the problem. After that, we'll build what I call a calculus bridge to handle the tougher part with a rod, figure out the force, and finally, we'll pack it all up into a neat little toolkit for you. Okay, first things first. Before we can solve anything, we have to be totally clear on what it is we're trying to find. So what in the world is gravitational potential energy? At its heart, it's just stored energy. Imagine you're lifting a book off the floor. The work that you do against gravity gets stored in that book as potential energy. The higher you lift it, the more energy gets stored, and it's just waiting to be converted back into motion if you drop it. It's all about its position. Now, let's talk about something that trips up so many students, that negative sign you always see in the formula. Why is it there? Well, it's a convention, but it's a really smart one. It tells us we have a bound system. Think of it like being at the bottom of a gravitational well. You have to add positive energy. You have to do work to climb out of that well and pull the two masses infinitely far apart. All right, with that foundation in place, let's apply this to the first part of our Irodov problem. Now, this part deals with a really simple case that should feel pretty familiar if you've taken any intro physics class. The problem starts us off easy. It asks us to find the potential energy between two simple point masses. We'll call them M1 and M2 that are separated by some distance r. And the solution? It's one of the most fundamental formulas in mechanics. The potential energy, U, is just the negative of the gravitational constant, gamma, times the product of the two masses, all divided by the distance r between them. And that's it. That's our answer for part A. But what happens when one of those nice, tidy little points gets stretched out into an object, like a long, thin rod? All of a sudden, our simple formula doesn't work. What even is the distance r anymore? The mass is spread all over the place. This is the real challenge of the problem, right? This is where Irodov really starts to test you. We can't just plug and chug with our simple formula. We need a much more powerful tool to handle this continuous blob of mass. The way we solve this is with a really powerful technique I like to call the slice and sum method. It's just 3 steps. First, we're going to mentally slice the rod into an infinite number of teeny tiny point-like masses. Then, we'll write down the potential energy for just one of those tiny slices. And finally, we'll use the master tool of calculus, integration, to add up the energies from all those slices. All right, enough talk, theory time is over. Let's get our hands dirty and actually put this slice and sum method to work and solve part B. So, first things first. Since the rod's mass is spread out evenly, we can define something called linear mass density, which we represent with the Greek letter lambda. It's super simple. It's just the total mass of the rod, big M, divided by its total length, L. It basically just tells us how much stuff is packed into every little inch of the rod. Now that we have that density, we can look at our conceptual slice of the rod. Let's say this tiny slice has a little length dx. Well, its tiny mass, which we'll call dm, is just that density, lambda, multiplied by its tiny length, dx. And there it is. That's our little point-like piece. So now we can use our good old point mass formula, but just for this one tiny piece. The potential energy of this slice, du, is going to depend on its mass, dm, and how far it is from our other mass, m. And listen up, because this is a pro tip. Be so careful with that distance. This is where almost everyone messes up. The distance from M to our little slice isn't just x. It's A, the distance to the start of the rod, plus x, the distance along the rod to our slice. Okay, so we've got the potential energy for one single tiny slice. To get the total energy for the entire rod, we need to add up the contributions from all the slices. And how do we add up an infinite number of tiny things? Well, that's exactly what an integral was invented for. We're going to integrate or sum up all those little du's, starting from the beginning of the rod at x equals 0, all the way to the end at x equals L. And after we turn the calculus crank, I'll spare you this step-by-step math, but it's a pretty standard natural log integral. We get our final answer. This is the potential energy between the point mass and the entire rod. It looks a bit more complicated, right? And see that natural log in there? That's a direct consequence. It's a signature of the fact that the mass is spread out over a length. Awesome. We found the energy. But wait, we're not done yet. If you remember the problem, it also asked for the force of their interaction. Luckily for us, in physics, energy and force are basically two sides of the same coin. And here it is, the fundamental connection. Force is simply the negative derivative of potential energy with respect to position. You can think of it like this. It tells you how steep the energy hill is. It tells you how quickly the energy changes as you change the separation between the objects. In our problem, that separation is the variable A. So to get the force, we just have to take the derivative of our energy equation with respect to A. So what does this look like? Let's put them side by side. On the left, you've got the classic inverse square law for 2-point masses. The force drops off with the square of the distance. But on the right, that's our new result for the rod. And notice, it's different. It's not a simple inverse square law anymore, because the total force is kind of an average of the pulls from all the different parts of the rod. Some parts are closer and some are farther away. Okay, we've covered a lot of ground. So what are the big key ideas you need to walk away with? Let's go ahead and assemble our Irodov toolkit for these kinds of problems. Here are the essentials. First, that negative potential energy means you have a bound system. Second, anytime you see an extended object, not just a point, that slice and sum integration method is your absolute best friend. Third, and I'll say it again, be so careful with your variables, especially that distance in your integral. It's the easiest trap to fall into. And fourth, always remember that powerful connection. Force is just the derivative of potential energy. And that's our deep dive into this classic Irodov problem. But I'm going to leave you with a final challenge, a little brain teaser. We solve this whole thing in one dimension, along a single line. But what happens if you move that point mass off the axis, say above the center of the rod? Suddenly it's a two-dimensional problem, and you're going to need vectors. How would you even begin to set up that integral? Give it some thought. Thanks for watching.